High above the Earth, where the air thins and the stars burn with unfiltered intensity, humanity has built a cathedral to the cosmos. Not of stone, but of steel and silicon, precisely tuned to capture whispers from the very edges of existence. This is the Atacama Large Millimeter/submillimeter Array, or ALMA. It stands as a testament to what we can achieve when we unite our greatest minds against the planet's most formidable challenges, all to unlock the universe's deepest secrets. Its journey, from a dream to a reality, is as breathtaking as the discoveries it now makes. ALMA is not a single telescope, but a giant interferometer, a network of 66 high-precision antennas working together as one. Unlike optical telescopes that see visible light, ALMA observes millimeter and sub-millimeter wavelengths. This allows it to peer through vast clouds of dust and gas that obscure visible light, revealing the coldest, most distant, and earliest objects in the universe. It's designed to study the formation of stars, planets, and galaxies, offering an unprecedented view into the processes that shaped our cosmic home. To achieve its extraordinary capabilities, ALMA needed an extraordinary location. The chosen site, the Chilean Plateau in Chile's Atacama Desert. At an astounding 16,500 feet above sea level, this arid, remote expanse offers the perfect conditions for sub-millimeter astronomy. The extreme altitude means the air is exceptionally dry, with minimal water vapor to absorb the faint cosmic signals. But this pristine environment came at an immense cost, transforming every aspect of construction into a Herculean task, pushing human and technological limits. Building at 16,500 feet isn't just difficult, it's profoundly dangerous. The air contains only about half the oxygen found at sea level. Workers and engineers, many of whom were local Chileans, had to undergo rigorous acclimatization protocols. Every task, from welding to operating heavy machinery, became an exhausting battle against hypoxia. Oxygen stations were mandatory, and shifts were limited to prevent severe altitude sickness. This wasn't merely construction, it was an expedition, where every breath was a conscious effort, highlighting the dedication required. Before a single antenna could be erected, an entire infrastructure had to be carved out of the desolate landscape. Roads were built across rugged terrain, power lines strung, and a complete operations support facility established at a slightly lower altitude of 9,500 feet. This base camp, vital for staff and antenna maintenance, served as the logistical heart for the extreme conditions above. It was a monumental logistical undertaking, transporting every bolt, every beam, every piece of equipment to one of the most inaccessible places on Earth, under the harshest possible conditions. The heart of ALMA's scientific prowess lies in its cutting-edge antennas. These are not just large dishes, they are instruments of incredible precision, manufactured to tolerances finer than a human hair, even though they weigh over 100 tons. Each antenna must maintain its parabolic shape with nanometer accuracy across wide temperature fluctuations and strong winds. This level of precision is critical for them to function together as one giant virtual telescope, capturing the faint, high-frequency signals from the cosmos with perfect alignment. To detect the incredibly faint millimeter and sub-millimeter waves from space, ALMA's receivers must operate at temperatures just a few degrees above absolute zero, colder than deep space itself. This requires sophisticated cryogenic systems, cooling the sensitive electronics to -269 degrees Celsius. This extreme cooling minimizes thermal noise, ensuring that the subtle cosmic signals are not drowned out by the instrument's own heat. Such advanced technology, housed within each antenna, represents a pinnacle of low-temperature engineering, vital for ALMA's unparalleled sensitivity. Once built, these massive, delicate antennas had to be transported from the operations support facility at 9,500 feet up to the high-altitude array at 16,500 feet. This was accomplished by two custom-built, 28-wheel transporters, nicknamed Otto and Lore. Each transporter is an engineering marvel in itself, capable of lifting and carefully moving a 115-ton antenna across treacherous mountain roads. The journey was slow, painstaking, and often took an entire day, a testament to the scale of the challenge in deploying ALMA across the plateau. The signals gathered by ALMA's 66 antennas are sent via fiber optic cables to the ALMA correlator, essentially the telescope's supercomputer brain. Located at the Operations Support Facility, it combines and processes the vast streams of data, performing quadrillions of operations per second. This complex machinery is what transforms 66 individual signals into a single, incredibly sharp image, effectively creating a telescope with a baseline up to 16 kilometers wide. It's the critical piece of technology that enables ALMA's high-resolution imaging capability. The sheer scale and complexity of ALMA meant no single nation could undertake it alone. From its inception, ALMA was conceived as a global partnership, a vision born from the shared desire to push the frontiers of astronomical knowledge. It began with early collaborations between North America, Europe, and East Asia, each bringing unique expertise, resources, and a collective commitment to science. This foundational agreement laid the groundwork for one of the most ambitious international scientific projects ever attempted, transcending political and geographic boundaries. Ultimately, the ALMA project became an unprecedented international collaboration, involving 66 nations. This grand alliance encompassed diverse expertise, from cutting-edge electronics manufacturers in Japan and Europe to advanced computing specialists in North America, all united under a common scientific goal. The host country, Chile, provided the invaluable site and local support, while contributing significantly to the construction and operation. This vast network of cooperation not only pooled financial resources but also integrated the best scientific and engineering minds from around the globe, making ALMA a truly universal endeavor. The collaborative spirit extended beyond funding. Teams of engineers and scientists from different continents had to learn to work seamlessly, overcoming language barriers and cultural differences. Specialized components, like the ultra-sensitive receivers, were developed and built in various partner regions, then meticulously integrated at the ALMA site. This distributed manufacturing model not only leveraged global expertise but also ensured the highest quality standards across all aspects of the observatory. It demonstrated a profound commitment to shared scientific progress. After years of challenging construction and integration, ALMA achieved its first flight in 2011, marking the beginning of scientific operations. Even with a partial array, early observations quickly demonstrated ALMA's unprecedented power. One of its first major successes was imaging the gravitationally lensed galaxy SDP.81, revealing fine details in the distant universe. These initial discoveries confirmed ALMA's potential to revolutionize our understanding of cosmic phenomena, proving that the immense effort and international collaboration were already yielding extraordinary results. One of ALMA's primary objectives is to understand how stars and planetary systems form. By observing the cold dust and gas clouds where stars are born, ALMA can penetrate the opaque envelopes surrounding protostars. It has provided stunning, high-resolution images of protoplanetary disks, showing nascent planets carving out gaps in the dust. These observations have challenged existing models of planetary formation, revealing that young planets can form much faster than previously thought, offering new insights into the origins of worlds like our own. ALMA has also become an indispensable tool for studying the most distant galaxies, allowing astronomers to look back in time to the early universe. Its sensitivity enables it to detect the faint, redshifted light from galaxies just a few 100 million years after the Big Bang. These observations provide crucial data on the conditions in the early cosmos, showing how the first massive galaxies assembled and began forming stars. ALMA's ability to map gas and dust in these ancient systems is helping to piece together the cosmic evolution of structure in the universe. Beyond star and galaxy formation, ALMA is making groundbreaking contributions to exoplanetary science. It can detect complex organic molecules in the protoplanetary disks around distant stars, the very building blocks of life. By mapping the distribution of these molecules, scientists can infer the chemical conditions and environments where new planets are forming. This provides vital clues about the potential for life to emerge on other worlds, pushing the boundaries of astrobiology and the search for extraterrestrial intelligence, one molecular signature at a time. While ALMA itself isn't designed to directly image black holes like the Event Horizon Telescope, it plays a crucial role in understanding their environments. ALMA observes the gas and dust swirling violently around supermassive black holes at galactic centers, revealing how these behemoths influence star formation and galactic evolution. It maps out the feeding habits of black holes and the outflowing jets that impact their host galaxies. Its high resolution and sensitivity are key to dissecting these extreme cosmic engines and their profound effects on the universe. The sheer volume of data produced by ALMA is staggering. When fully operational, the correlator processes raw data at a rate equivalent to continuously streaming all the Netflix movies in the world, multiple times over. This torrent of information requires immense computational power and sophisticated data archival systems. Every astronomer worldwide can access ALMA's vast data archives, ensuring that this $1.4 billion investment continues to yield new discoveries for decades, furthering our collective understanding of the universe through open scientific inquiry. ALMA is more than just a telescope, it's a profound statement about humanity's drive to explore. It stands as a symbol of international collaboration, demonstrating that our greatest aspirations can be realized when we unite across borders, cultures, and disciplines. The construction challenges were overcome by ingenuity and perseverance, the cutting-edge technology continues to define new possibilities, and the stream of astronomical discoveries ceaselessly redefines our place in the cosmos. Its legacy will inspire generations, proving that even the most ambitious dreams can be built, one antenna at a time, at the very edge of space.